Our goal with this discussion is to begin to understand inverse functions. But before we do that, we need to figure out what an inverse is and get a little bit of an understanding of an inverse relation. And then we'll quickly step into inverse functions. So first of all, what is an inverse? Well, when you go from the output of a relation back to its input, when you sort of reverse the process and go in the opposite direction, then that is the inverse of the relation. For example, let's say that relation H was defined in the simplest possible fashion, and that is with some ordered pair. So -8 input had an output of 5. A 4 input had an output of -2. A -7 input had an output of 1, and maybe one more. A 3.8 input had an output of 6.2. Now, we do not need to worry about how the input generates the particular output. We're not trying to look for an equation or something like that. We just want to understand if this is the original relationship H, then what would the inverse of H look like? Well, the output of 5 would bring back the input of -8. So 5 was the old output. It was the output in the original H. It's now the input for the inverse of H. And the the 4 -2 would become a -2 4. The -7 1 would become a 1 -7. And the 3.8 6.2 would become a 6.2 3.8. Right? So inputs become outputs, outputs become inputs. More simply put, X and Y trade places. If you think of inputs and outputs like most people in an algebra setting will do, if you think of inputs and outputs as X's and Y's, then in the case of an inverse relation, the X's and the Y's simply trade places. And that's something you're going to want to really take to heart. You're going to write that down and remember it, is that when you move to an inverse from the original relationship, X and Y trade places. All right. So something else that's going to come up. This is what it looks like. This is the appearance it takes on when you're looking at ordered pairs. Graphically, if you're looking at a relation versus its inverse, what's that going to look like? Well, if you look at the line y equals x, first of all, keep that line in mind. Note that any ordered pair that was in the original relationship that's on that line will stay put, because on that line X and Y are exactly the same. So switching them around will change nothing. All right. But on the other hand, if you had something on there like a 2, 4, if that's in your original relationship, then 4, 2 will be in the new relationship. If you had something on there like a 0, 3, then 3, 0 will be in the new relationship. And it may be a little bit hard to see just from my drawing, but what actually happens is when you move from an original relationship to its inverse, points will mirror, will flip across this line y equals x. In other words, if you were to turn it into that orientation, to where the line y equals x looks kind of vertical, then you will see that the original and its inverse are the mirror image of each other across that line. So replacing a relationship with its inverse graphically has the effect of mirror imaging across the line y equals x. That's the way it works when you're just listing ordered pairs, you switch X and Y. That's the way it works. When you're graphing, you just switch X and Y. And if you had a relation in equation form, if I had something like y equaling x squared minus 5x, if that's the original relation, if that is the original, then the inverse of that relation would simply be x equal to y squared minus 5y. Again, the x and y simply trade places. They just exchange. All right, so here the x is the original input, this y is the output, and over here they have traded places. All right, so again, moving from relation to its inverse, x and y simply trade places. Now, what we need to look at next is a certain type of function. All right, there's a specific type of function that we're going to be working with when it comes to these inverses and our beginning of our discussion of inverse functions. So let's look at some ordered pairs. And instead of just writing them out in ordered pairs, I'm going to put them in a table. And what I want to look at is a year versus the cost of a stamp. The prices of stamps have risen over the years. And if you look at, for example, 1996 and 1998, in both of those years, a stamp cost 32 cents. If you look at 2000, the price of a stamp rose to 33 cents. If you look at the year 2002 and the year 2004, through that entire time frame, stamp was 37 cents. In 2006, the price of a stamp went to 39 cents. And I'm not going to sit here and list out everything through 2020. I think you get the idea that there is a relationship here. All right. Now, for comparison, let's look at an entirely different scenario. Let's look at a number versus its cube. When you take -3 and you cube it, you get -27. When you take -2 and cube it, you get -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. So again, here are two relations for us to look at. And with one of them, when I go to turn it around, something interesting happens. If I take this relationship here right above, and I go from cost of stamp back to year, when I reverse that process, the 0.32 will go back to both 1996 and 1998. The 0.33 goes back to nothing but 2000. The 0.37 maps backwards to 2002 as well as 2004. And the 0.39 maps back to nothing but 2006. Now, if I take the other one and find its inverse, -27 will map back to nothing but -3. -8 goes back to nothing but -2. -1 goes back to nothing but a -1. 0 is back to 0. 1's back to 1. 8's back to 2. 27 is back to 3. Now look what we've got happening here. All right. For comparison and contrast purposes, look what we've got. This was a function. In the beginning, I had a function. Every input had a unique output. Input, unique output. Input, unique output. This was a function, so was this. All right, both of these are functions. But when I go and obtain the inverse, look what happens. The one on the left was a function, its inverse is not. This input doesn't have a unique output. This input doesn't have a unique output. All right, making this not a function. So I had something that started as a function, but as soon as I found its inverse, not a function anymore. On the other hand, this one was a function, just like the first, and its inverse is 2. All right, so we need to be able to identify which functions are going to have inverses that are functions as well. And when that's going to happen is when we have what's known as, and what this one is a 1, 2, 1 function. If your function is 1 to 1, then when you reverse it in search of its inverse, then that inverse is going to be a function as well. And what it means for a function to be 1 to 1 is that every output has to have a unique input. Now, that makes the definition of function and the definition of 1 to 1 easy to get confused, easy to get backwards. All right, so let's talk about both. To be a function, input has to have unique output. Input, unique output. Input, unique output. Just like over here. Input, unique output. Input, unique output. That's what it takes to be a function. Every input has a unique output. But to be 1 to 1, every output has to have a unique input as well, which the one on the right did have, the one on the left did not. All right? There are a couple of ways to spot a 1 to 1 function. And be aware that being a function and being 1 to 1 are basically independent of each other. You can be one, you can be the other, you can be both, you can be neither. All right? So let's look at, for the sake of comparison, a couple of parabolas. There's one. Over here's another one. All right? One of these is a function. One of them is not. The way you've been taught to spot them is through something called the vertical line test. And it's a extremely good technique if you have a good graph in front of you. For example, on this particular parabola, I can draw a vertical line right here and strike it more than once. So this is not a function. All right, now this parabola, no matter where you draw a vertical line, you can't hit it more than one time. All right, so this parabola is a function because this one passed the vertical line test, this one failed it. There is another test called the horizontal line test. And the graph on the right fails the horizontal line test. I can draw a horizontal line and I can hit it more than once. That means it is not 1, 2, 1. Whereas the graph on the left, I can draw a vertical line, a horizontal line anywhere I want, and I won't hit it more than once. So this is 1, 2, 1. All right, what that means is this is a function. The one on the right is a function, but its inverse will not be. This is not a function, but its inverse will be. What we would really like to have are functions, therefore relationships that pass the vertical line test, that also pass the horizontal line test. When you're looking for inverses, what is highly, let's say highly desirable, are relations that pass both vertical and horizontal line tests, making them not just functions, but 1 to 1 functions. We want it to be a function, and we want it to be 1 to 1 as well, right? So if I was to draw a graph, you should be able to look at a graph and quickly and easily spot one-to-one functions. For example, there's an exponential growth curve, okay? That curve will pass both the vertical, draw a vertical line wherever you won't hit more than one of it, and horizontal, okay? So your exponential growth is a 1, 2, 1 function. That means it has an inverse that is also a function. Your reciprocal function, y equal 1 over x, looks like this. And again, it will pass the vertical line test. No matter where you put a vertical line, you will not touch it more than one time. So it is a function, and it will pass the horizontal line test. No matter where you put a horizontal line, you'll only touch it once. So this one is also 1, 2, 1 function. All right. Your parabolas, whether they're graphed right side up or upside down, they're going to pass the vertical line test. They're going to be functions. They're not going to be one-to-one. So how else can we test for one-to-one? How else can that be done? Well, it can be done algebraically, which is a little bit trickier, all right? But it can be done. So when you test for one-to-one algebraically, what we're testing to see is with a 1-to-1 situation, you will find that if f of a equals f of b, in other words, if the outputs are equal, then it can only happen if the inputs were equal. All right, so for example, I just said that a parabola is going to tend to not be one-to-one. So let's make f of x equaling x squared. All right, then f of a equaling f of b means a squared equals b squared. And as I work to simplify this, I'll take the square root of both sides. I'll extract roots here. And remember, when you extract roots, you have to throw on that plus or minus sign. So my conclusion was that a could have been equal to b, or a could have been the opposite of b. That's why this is not 1-to-1. Okay. Whereas, on the other hand, if h of x is equal to a 3x plus a 5, then h of a is a 3a plus 5, equaling h of b, which is a 3b plus 5. When I work to simplify this, I will subtract 5 from both sides, divide both sides by 3, and the outcome of that is a equals b. The only way for these two to be equal is if a and b were equal all along. So that means this particular linear is in fact 1-to-1. All right, so that's your basic test for one-to-one. You can test graphically, or you can test graphically with the horizontal line test, or you can test algebraically, with the algebraic test being, frankly, usually the more difficult of the two. All right, so with all that being said, let's just throw in a couple more practice problems, shall we? Okay, for example, if they were to ask you to take 2x squared plus 5y squared equaling 4, if that is the original relation, then what will the inverse of the relation look like? Again, remember, when you move from a relation or a function to its inverse, what happens is x and y trade places. So this will become a 2y squared plus a 5x squared equaling 4. Now, when you're moving from a relation to its inverse, it's nice, whenever possible, to solve for the new y. Again, the new y not being the same as the old y. This y used to be x. It's nice to solve for it when you can. This is a situation where that's not particularly convenient. All right, not particularly convenient, so we won't do it. Now, if you had something like x equal 1/2 y plus 7, if that was your original relation, when you move to your inverse, you're going to have y equal 1/2 x plus 7, and that's good. That's solving for y. It's been basically done for you, so that's quite convenient. All right, and again, proving one-to-oneness using the definition is not particularly hard. You just have to remember, if you have something like a root, for example, if you had an f of x equaling cube root of x, and you wanted to prove that it was 1-to-1, you would just say, well, cube root of a equals cube root of b. To get rid of the cube root, you cube both sides. And remember, when you square root both sides, you have to introduce that plus or minus, but when you cube, you don't. All right, so proving this function to be 1-to-1 was not difficult. The graph of it would have been helpful. The graph of that cube root function looks like that. The calculator could have shown that to you, and you would have clearly seen that it passes both the horizontal and vertical line test. And from that, you would know that it has an inverse that is itself a function. All right. So with a few of these problems, they're going to throw in for you a process where you have to both decide whether it's 1-to-1 or not, and if it is, find the formula for the inverse. We've covered all those steps. It'll just be up to you to piece them together within the context of a single problem.